So welcome you back to today's module. So let us try to revisit what we did yesterday or in the last few modules. So we started with invariant testing. So the problem is as follows. I have a data which could be a random sample or even dependent. You can have a dependent structure where x1, x2, xn need not be independent. This has a joint PDF or PMF F which belongs to a family P. Now suppose this family P is partitioned into two sets P0 and P1. So you have P0, P1 subset of P. They are non-empty. They are disjoint and their union is whole of P. And what you're interested in testing is H0, that F is a member of P0 against the alternative hypothesis that F is a member of P1. Now as I said, the advantage of studying invariant tests is that many times my testing problem might have a nice structure. Now if it has a nice structure, then my test procedures should also have nice structure. And that may reduce the class of all tests which one needs to consider. Once the class of tests is restricted, then finding a best test within that class may be possible in certain situations. So suppose G is a group of transformations. Acting on sample space essentially, but you can say that this is on Rn because your data is in Rn. Essentially, G would be acting. Elements of G would be acting on sample space. What I assume is P0 and P1 are invariant under G. That means if X has a PDF in P0, then y is equal to gx would also have a PDF in P0 only. Similarly, if x has a PDF in P1, then y is equal to gx would also have a PDF in P1 only. So in that sense, P0 and P1 are invariant. If that happens, I say that my testing problem is invariant. So now suppose that you have an invariant testing problem. What does it say? That when I apply transformation gx to x, gx has some distribution. Then the alternative hypothesis says that gx is also in P0. Alternative says that gx is also in P1. So that means when I transformed x to gx, my null hypothesis and alternative hypothesis do not change. So that means if I was rejecting H0 in the earlier situation, I should reject H0 in the later situation, which is a transform problem. Or in other words, if I was rejecting H0 with certain probability in the earlier occasion, untransformed problem, I should be rejecting H0 with the same probability in the transform problem. So I said a test procedure, a test phi, which we have defined to be a function from Rn to 0, 1, with the interpretation that phi of x denotes the probability of rejecting H0, and 1 minus phi x is probability of not rejecting H0. So as test phi is said to be invariant under G if phi of gx is same as phi of x for every x belonging to R and for every G belonging to G. So my invariance principle demands that I should consider only invariant tests. So I denote di alpha. So alpha is a given level of significance. I define di alpha to be collection of all those phi's such that phi is invariant under G. and it has label alpha. That means probability of rejecting H0 is always less than or equal to alpha for every f in P0. And then I try to find a test which has a maximum power among the tests in di alpha. And I call that test as UMPI alpha test, uniformly most powerful invariant test of label alpha. Now what we decided, or what we proved was, if your phi is invariant, then the distribution of phi depends on a maximal invariant functional. So distribution of phi, which is invariant, that means it belongs to di alpha, depends on f only through maximal invariant functional theta f. So what is a maximal invariant functional? That means it should be invariant. So that means theta of g bar f. G bar is the group of transformations induced by this group of transformation on P. So it says that theta of g bar f should be same as theta of f for every g and for every f. And if theta f1 is same as theta f2, then f1 and f2 should be related through some g bar. So what it says? That means first, my invariance principle demands that I restrict to only those tests which are in di alpha. But any test in di alpha depends on f only through theta of f. So that means I have to see what is the corresponding null hypothesis in terms of theta f. So many situations, this theta f would be real valued, and these hypotheses should get transformed in terms of theta f in such a manner that I am able to find the best test. And that would be UMPI alpha test. So we considered one example last time, which was for testing whether data is in a given location family against that it is in some different location family. Now today we'll do the same exercise for the scale families. So let us consider this example. So my Pi, which I want to test, so my Pi I0 and P1 are this, are Fi theta. So I represents this I, so that means under P0 it is F0 theta, where theta belongs to capital theta, which is 0 to infinity, where Fi theta x is some kind of a scale family, so that means it is 1 by theta to power n. Fi, again depends on I is there, because under P0 and P1, I may have a different Fi. X1 by theta, xn by theta. X belongs to Rn, theta belongs to theta, and I is equal to 0. So under P0 I have a different scale family, under P1 I have a different scale family, and I know that scale family is invariant under scale group of transformation or under the multiplicative group. So G I consider as collection of all those GCs such that GC of x1, x2, xn is same as C of x1, x2, xn for every x belonging to Rn, and C is positive. So whether you apply this G to P0, which is some scale family, or P1, which is again some different scale family, P0 and P1 would be invariant under G. That means if x has a distribution in P0, that means F0 would be here. Y is equal to Gx would again have a, GCx would again have a distribution over here, except that this Fi remains the same. This theta just gets changed to C theta. So Pi is invariant under G with What is the induced transformations? My induced transformation is G bar C F I theta, you have to write down. G bar F C I theta, F I remains the same, and then C theta. So this we know, right? X theta just gets changed to C theta. So P0 and P1 are invariant. So I need to consider only invariant tests. So I need to see what is the structure of a invariant statistic. A statistic Tx, so Tx is invariant if and only if T of GCX should be same as T of X, or T of X should be same as T of GCX, so that means T of x1, x2, xn, xn minus 1, xn should be same as T of Cx1, Cxn minus 1, Cxn for every x belonging to Rn and C positive. So I have 1 degree of freedom available with me, which is in terms of this parameter C. But C has to be positive. So I can choose C to be 1 upon mod xn. Note that C I require to be positive because PDF will turn out to be x1 upon C theta, xn upon C theta, and here C theta to power n. I needed C theta to be positive, and theta is given to be positive, so that requires C to be positive. So this means T of x1 upon mod xn, xn minus 1 upon mod xn, and xn upon mod xn. So any invariant statistic has to be a function of this, which is x1 upon xn, xn minus 1 upon xn, and xn upon xn. So let me call those quantities as T of R1, Rn minus 1, and Rn, where Ri is nothing but xi upon mod of xn. I is equal to 1 to n. But as we did in the case of estimation, x1 upon mod xn, xn minus 1 upon mod xn, xn upon mod of xn is a 1-to-1 function of x1 upon xn, xn minus 1 upon xn, and xn upon mod of xn. So this would be, I can write down this in terms of x1 upon xn, xn minus 1 upon xn, and xn upon mod of xn. That is very simple. Suppose you consider this. I have to show that one is a function of other. So that means I have to show that if I know one, I know the other one. So suppose I know this. I know this, then I also know that xn upon mod of xn, whether it is positive or negative. If I know that whether it is positive or negative, I know what is x1 upon xn is. Because if xn is positive, it would be minus x1 upon xn. So if I know minus x1 upon x1, I know x1 upon xn. And conversely. So it is a function of x1, x2. So this is nothing but z1, z2, zn minus 1, zn upon mod h. z1, z2, zn minus 1, and zn, where zi is nothing but xi upon xn for I is equal to 1 to n minus 1, and zn is nothing but xn upon mod x. So any invariant statistic is a function of z1 upon zn, sorry, x1 upon xn, xn minus. So what it says is any invariant statistic is a function of x1 upon xn, xn minus 1 upon xn, and xn upon mod of xn, which you may call as z1, z2, zn minus 1. And also this is invariant. Why? Because if you apply C to everything, Cx1, Cc gets cancelled. Here also Cxn minus 1, Cxn, Cc gets cancelled. Here Cxn and mod of Cxn, C is positive, so C will come outside, Cc gets cancelled. So this is also invariant. And so this is also invariant. So what does that mean? That means this statistic is maximal invariant. So this implies that Z, which is Z1, Z2, Zn minus 1, Zn is maximal invariant. Now note that under Pi this is ancillary because its distribution will not depend on theta. I can divide both by x1 by theta and xn by theta. If I divide both by x1 by theta, I get a density Fi of Z1, Z2, Zn. So if my x is in Pi, this is ancillary, so that means it does not depend on theta. So what I need to do? I need to consider a test based on Z only. In Z, note that although the variables Z1, Z2, Zn minus 1, which are x1 upon xn, xn minus 1 upon xn, they would be continuous if x1, x2, xn are continuous. But xn upon mod of xn takes discrete values. It takes either the value minus 1 or plus 1. So what I do is, I try to find out first what is a joint PDF of Z1, Z2, Zn minus 1 and xn. So, or in other words, I can find the joint distribution of Z1, Z2, Zn minus 1 and Zn. So what is the probability that Z1 is less than or equal to Z1? Zn minus 1 is less than or equal to Zn minus 1. And let us say Zn is minus 1. Right? Z1, Z2, Zn minus 1 are continuous random variable, and this is. So what is this? This is same as. So under Pi, under let us say f having Fi theta. Right. So if you want, you can write down P Fi theta. What is Z1? Z1 is nothing but x1 upon xn less than or equal to Z1. Xn minus 1 upon xn is less than or equal to Zn minus 1. Zn is equal to minus 1. That means xn is negative. Is less than 0. So I need to find out what is the joint density of Z1, Z2, Zn minus 1 and Zn first. So joint PDF Z1, Z2, Zn minus 1 and not Zn, let's say xn, because Zn is a discrete value, is, what is the joint PDF? I can write down that as, let me write down this as h of Z1, Z2, Zn minus 1 and xn, let me put at t. Joint distribution of under Fi theta is given to be this. So what would be this? Jacobian term would be nothing but Z1 is, so what I am doing is Z1 is x1 upon xn is same as Z1, x1 upon xn is same as xn minus 1 upon xn is same as Zn minus 1, and xn I am finding at point t, right? So that means x1 is same as Z1t, xn minus 1 is same as Zn minus 1t, and xn is same as d. So when I look at a Jacobian term, I get upper triangular or lower triangular matrix. N minus 1 diagonal elements are Z1, Z2, Zn minus. When you put Z1, Z2, so N minus 1 diagonal elements, I get t, and the last diagonal element is 1, so it get mod of t to power n minus 1. That is a Jacobian term. Then Fi 1 by theta to power n, right? 1 by theta to power n. So under f theta I am doing Fi of x1 by theta, x2 by theta, and xn by theta. So that is Z1 t by theta. Zn, xn minus 1 is Zn minus 1 t by theta. And xn t by theta. So this is the joint PDF of x1, x2, xn, and then Jacobian term you have already written down, mod of t to power n minus 1 t by theta. Z, which is z1, z2, zn minus 1, belongs to Rn minus 1, and your t belongs to R. So I have to get this probability. So in this probability, probability that, so probability under Fi theta of z1 less than or equal to z1, zn minus 1 less than or equal to zn minus 1, and zn is equal to minus 1. That means xn is negative. That means here t would go from minus infinity to 0. Z1 goes from minus infinity to Z1 and so on. Minus infinity to Zn minus 1. Mod of t to power, then the density mod of t to power n minus 1 by theta to power n. Fi Z1 t by theta. Zn minus 1 t by theta. T by theta. Dt. If you want, I can make the transformation t by theta is equal to t prime. Then dt by d theta would go in Jacobian. So here theta to power n minus 1 would be left because 1 theta would go in Jacobian. Then it is mod of t by theta to power. So that would be mod of t prime to power n minus 1. So accept that. Now t is negative. So what I can do is I can make it minus t by theta is at t prime. So that t is negative, so range of t prime would become from 0 to infinity. So this becomes 0 to infinity, minus infinity to z1, minus infinity to zn minus 1. And then 1 by theta goes in Jacobian. Then mod t is how much? T is nothing but minus theta mod t, right? So that becomes t to power n minus 1. Fi, now t by theta is minus t prime, so minus z1 t, minus zn minus 1 t. I have first applied t prime and then I have converted t prime to t because t is an integrating variable, and minus t. So this is what my PDF under Fi theta turns out to be. So I can call this as Hi of, so I have a density, right? So this is capital Hi. Its PDF suppose is small hi. Now I see what is under, so that means under H0, my F is Fi theta. F belongs to, F is some Fi theta, which means these Z1, Z2, Zn minus 1 have this Hi, PDF. So F gets transformed to Hi. Now similarly I can find it out when Zn is plus 1 because Zn can take discrete values minus 1 or plus 1. So similarly P Fi theta Z1 less than or equal to Z1, Zn minus 1 less than or equal to Zn minus 1. Zn is equal to 1. What would happen? Exactly the same, this PDF would still be there, except that now t, which is a probability xn greater than positive, so which is same as probability Fi theta, Z1 less than or equal to Z1, Zn minus 1 less than or equal to Zn minus 1, and xn positive. So what would happen? Same thing over here, except that this gets converted to 0 to infinity. If it converts as 0 to infinity, I don't make any transformation, I make t by theta as t prime. So density becomes t by 2 power n minus 1, Fi of Z1t, Zn minus 1t, and Zt. So this is same as 0 to infinity, minus infinity to Z1, minus infinity to zn minus 1, t to power n minus 1, fi y1t, yn minus 1t, t dy1 dyn minus 1, and dt. There would be dy1, dy2, dyn minus 1 here also, because these integrals are there. So dy1, sorry, I can make it another variable y1. Because this has to be integrating variable, right? So dy1, because these z1, z2, zn minus 1 are fixed. So I'm integrating this vector dy1, dyn minus 1. So here also dy1, dyn minus 1. So this is this. So again, this denoted by zi, hi, which has a PDF. Let us say hi. Note that the PDF of hi does not depend on theta. So what does your transform h0 turns out to be? h0 is that my PDF h is same as f0, sorry, h0. h1 is that h is same as h1. But h0 and h1, because f5 was known, so this PDF is completely known, or this distribution function is completely known, so PDF is completely known. So what do you get by Neyman-Pearson lemma? Now one thing is, so what I need to write down is, I need to write down my PDF hiz. Of course, it will depend on whether zn is plus 1 or zn is minus 1. So this is same as 0 to infinity t to power n minus 1 fi of minus z1t, because when I talk about density, I have to integrate with respect to z1, z2, zn minus 1. Last is a discrete variable, so zn I write down as minus 1 only. So it is a mixed kind of a PDF. First n minus 1 variables are continuous. The last one is taking only value minus 1 or plus 1. So this is same as t to power n minus 1 fi of minus z1t. I have differentiated with respect to z1, z2, zn minus 1. Last one is a discrete, so that I don't have to differentiate, that I put value as it is, minus t dt. This is for the situation where the last variable is minus 1, zn is minus 1. So z belongs to Rn minus 1 and zn is minus 1. This is same as 0 to infinity t to power n minus 1 fi of minus z1, sorry, this would be z1t from here. Fi of z1t, zn minus 1t, t dt, z belongs to Rn minus 1 and zn is equal to 1. So the problem reduces to that of, if I restrict only to invariant tests, my problem reduces to that of testing a simple hypothesis against a simple hypothesis, because h0 is completely known to us, theta is gone. So let us try to see whether these two can be written in the same form. So note that, it would be hi capital Z upon h0z greater than c would be the rejection region. But for zn less than 0, right, that is this situation, hi of z1, z2, zn minus 1 zn is nothing but 0 to infinity t to power n minus 1 fi minus z1t minus zn minus 1t minus t dt, which is same as 0 to infinity t to power n minus 1 which is equivalent to zn is negative, that means Zn is, for Zn is equal to minus 1. For Zn is equal to minus 1, which is equal to saying that xn is negative, right? So the same as t to power n minus 1, fi of Z1 is minus x1 upon xn t. Minus xn minus 1 upon xn t and minus t dt. So what I do is, here xn is negative. So I make the transformation minus t upon xn as t prime. Again I'll replace t prime by t. So dt becomes t times xn. So dt becomes t times xn. So one xn would come with a modulo sign, and t is, so this would become modulus of xn to power n. Is that okay? Note that xn is negative. So what would be the range of t prime? When t is 0, xn being negative, it will be 0. When t is infinity, xn is negative, so this would also be infinity. Because minus xn is positive, so this would be 0 to infinity. Then here t was positive, so that is why t would be modulus xn t prime, so xn to power n, because xn is negative, right? So I just made that transform. So fi of x1t, xn minus 1t, and minus t is same as xn t. And under Zn is equal to 1, also you get the same thing. That is equivalent to that xn is positive, hi z, hi z1, z2, Zn minus 1, Zn. I do the same thing, x1 upon xn, but here xn is positive. So I can take t upon xn as t prime, no change of sign takes place, and you exactly get the same thing. Because Z1 I write down as x1 upon xn, so t upon xn, but xn is positive, so I put t upon xn as t prime. Range remains the same, and here again you get modulus xn. Modulus xn is same as xn because xn is positive. So this becomes modulus of xn to power n, 0 to infinity, fi of x1t, xn minus 1t, xn t dt. So what I'm trying to say is whether xn is positive or xn is negative or Zn is 1 or Zn is minus 1, my hi has the same form, which is modulus of xn to power n, 0 to infinity, fi of x1t, xn minus 1t, xn t dt. So that means by Neyman-Pearson lemma, the best test for testing H0 versus H1 is reject H0, H1 upon H0 is greater than C. So using Neyman-Pearson lemma, UMPI alpha test is phi naught x, which is, you see, mod of xn to power n minus 1 under hi and h0 would get cancelled. So it is 1 if 0 to infinity f1 of x1t, xn minus 1t, xn t dt divided by 0 to infinity f0 of x1t, xn minus 1t is greater than C. This is same as gamma if this is equal to C, and 0 otherwise, where C is chosen such that EF0, E under H0, which is same as E under F0 of phi of naught x is same as alpha. So we have found out the UMPI alpha test. So now the remaining exercise is for the affine group of transformations. That means situation where you are dealing with the location scale families of distributions. So that example we'll do in the next module. So this is all for today's module. Thank you very much.